Now let's start our topic of cyclic heat engine. Now for engineering purposes, the second law is best expressed in terms of conditions which govern the production of work by a thermodynamic system operating in a cycle. So we need a system which operates in a cycle. And a heat engine cycle, let me write it down. Alright, it's a thermodynamic cycle in which there is a net heat transfer to the system and net work transfer from the system. So this is very important. That is, it would have the first case, that is the net heat transfer to the system, okay, and the second is that you will have some net work transfer, okay, from the system. So you will have some positive heat and positive work. So these are the two main characteristics of a heat engine cycle. Okay, and the system which executes a heat engine cycle is called a heat engine. As simple as that. Alright. Now, how do you define a heat engine? A heat engine may be in the form of a mass of gas like this, which is confined in a cylinder and the piston machine. So this is the cylinder, alright, and this is the piston. So this mass of gas, this can be termed the heat engine, or it can also be a mass of water, like in this case, which is in a steady flow through a steam power plant. So this is also a heat engine, and this is also a heat engine. Now we'll analyze both of them one by one. In the cyclic heat engine, represented by this diagram, okay, heat, let us say Q1, so heat Q1, okay, is transferred to the system, and in effect of this heat transfer, there is some work that is done by the system, and that is WE, that is the gas would expand, so it becomes expansion work, WE. Alright. Now, when work WC, so let us say WC is the compression work, when it is done upon the system, there is some heat that is rejected from the system. So this is in conjunction to the you can say the distinction between heat and work. So when you supply heat as input, you get expansion work as output, but when you supply compression work as input, you get some heat rejection as your output, which is not useful, but of course, okay. Now, if we talk about the system, and this only system, we stay on this system before we move on to this system, that is the steam power plant. And if this system is brought back to the initial state through all these four successive processes, so it will make a heat engine cycle. So you have four processes. The first process in this case is the supplying of heat as Q1. The second process is the expansion work that comes out of the system. So this is a pair of two processes. The next pair of processes would be the supply of work as compression work, WC, and some heat rejection as Q2. So these four processes in combination create a heat engine cycle, which we call a heat engine of this sort. Alright. Now if you talk about the heat engine depicted in this diagram, okay, so this is the boiler in which there is some input of heat. Let us say that input of heat is Q1, and you get the water vapors which flow through this pipeline into a turbine. The turbine gives us some work output, that is the WT, the shaft work output. Now the condensate will now go into the condenser, which will reject some heat. So let us say that the heat rejection is Q2. Now this condensate which comes into a pump has to be put back into the boiler, so you'll have to provide some work input, and that is the pump work. Okay, so I will now talk about this thing, that is Q1. Let's talk about the system and let's define these terms, Q1, WT, Q2 and WP. So Q1 is the heat input to the boiler. Alright. Now this hot vapor or this hot steam goes into turbine and you get some turbine shaft work output. This is the work output from turbine. Okay, and then you have Q2, which is the heat rejection from the condenser. Alright, let's move it up a bit. And WP is the work input for pump, or the condensate handling pump. Okay, now this is actually a cycle which is repeating itself. Okay, so for a cycle, let's find out the net heat transfer and the net work transfer. Alright, so net heat transfer is the difference between the heat supplied and the heat rejected. So Q1 minus Q2. Let us say this is equation number 1. The net work transfer in this cycle would be the output work, that is WT, minus the pump work. Okay, so this is equation number 2. I think you understood this much. Now, if you invoke the first law of thermodynamics for the case of a cycle. So for a cycle, the first law would be that the net heat transfer is equal to the net work transfer, and this is for a cycle. Alright, so this makes it that Q1 minus Q2 is equal to WT minus WP. So this is a relation which represents a cyclic heat engine. Okay, so this is a very simple analysis of this cyclic heat engine. Now after this analysis, we come to a very important question, or very important term, I must say, that what is the purpose or the function of a heat engine. Okay, now the function of a heat engine cycle, I must say, that is a heat engine cycle. Okay, it is to produce work continuously at the expense of heat input, at the expense of heat input. So this is the primary function of the heat engine cycle. So as per this definition, as per this statement which indicates the function of a heat engine, the terms of primary interest are the net work output, let me use some other color, the net work output and the heat input. So two things which are of primary interest to us is the net work output and the heat input to this cyclic heat engine, because the ratio of the net work output upon the heat input, this gives us the efficiency of the heat engine or the heat engine cycle. So this gives us the efficiency of the heat engine. Okay, so this is equal to WT minus WP by Q1. Now this equation is also equal to Q1 minus Q2. So it is equal to Q1 minus Q2 by Q1, and we can say that efficiency of heat engine is equal to 1 minus Q2 by Q1, and it is obviously less than 100%. Okay, now after this let's talk about the energy reservoirs, okay, in which we'll talk about the heat source and the heat sink. So in this video we talked about what a heat engine is and what a heat engine cycle is. So we need to take care of two things in a heat engine cycle, that is net heat transfer to the system and net work transfer from the system. Alright, and the primary terms that we are concerned about is the net work transfer and the heat input. Now this is the efficiency of the heat engine, which is but obviously less than 100%. Alright, so how can we maximize it, or how can we make it, almost equal to 100? But of course we cannot make it equal to 100, but how can you bring it closer to 100? That is to either increase the heat input or to decrease the workout or the heat rejection. So let us summarize some points before we go on to the next video about increasing the efficiency. So the first thing I can do to increase the efficiency is to increase the net work output. That is either by increasing the turbine work output or by decreasing the pump work input. Okay. Second thing that I can do is to increase the, you can say, heat input. Now heat input increment is not always advisable for the sake of keeping the cycle economical, because then you'll have to expend a higher amount of energy, which is not always economical while running a very big system. The third thing that we can do, and which is very advisable, is to reduce or decrease the heat rejection. Okay, so if you are able to extract maximum possible net work out of the system, that is the if you are able to increase the work output from the turbine, it would automatically reduce the heat rejection, because most of the energy would be consumed in giving you the shaft work. Okay, so your Q2 will automatically decrease. So these are some things or some steps we can take to maximize the cycle efficiency. So I hope you understood this whole video and the concept of the cyclic heat engine and how do we look at the efficiency of a heat engine. Now let's go to the next video and talk about energy reservoirs and look at what is a heat source and a heat sink.